Hello everyone and welcome back to another video. Today we have a new update which is called Grand Collision Unification. I don't know what unification means, but actually I have no idea what it means. Like, I can't even guess. But let's just read about it. Unified collisions. Shockwaves propagate across gas giant surfaces, and fragment ejection direction is more realistic with our new unified collision system, which combines our two previous separate collision methods. Saving your interface. Pick right up where you left off with the Properties panel opened. Save simulations. Now remember the state of the interface panels. Okay, see it in action. I don't want this to be autosaved, but in this simulation, Earth has recently been tidally locked with the Sun. The Earth is now rotating once per year, so that side of the Earth will always be facing the Sun, and the opposite side will always be facing away towards the darkness of space. The side facing the Sun will heat up until the ocean is nearly at the boiling point of water. On the other side, snow will pile up and the ocean will eventually freeze. Open Earth's surface tab or multiple data views to watch how Earth's temperature and surface changes over time. Okay, tidal locking is a phenomenon that can occur naturally over time as gravity shows the rotation speed of one object orbiting another. In real life, the closest example is Earth's moon. I actually know that, which rotates at the same speed it orbits the Earth. This is why we never see the far side of the moon from the Earth's surface. So it's a little piece of information for the people who didn't know that, but there you go. That's the Earth tidally locked. And if we save this, once it saves, it will, if we open it back up again, I'm pretty sure it's going to, yeah, it keeps this. It just doesn't keep this. That's a bit weird. Anyways, let's see what else is new. Evidence for a signal generated from all supermassive black hole pairs from across the universe was announced on June 28, 2023. Learn how this evidence was found and explore the galaxy-sized detector that was used. Okay, that's the end thing. So, see the dwarf planet's Quaoar's newly discovered rings. Okay, it's really far away from the Sun. Okay, so it has really thin rings, but they're rings. Alright, let's read. Quaoar is a dwarf planet discovered in 2002 that orbits the Sun beyond Pluto's orbit. Oh, it has a moon? Way what? Okay. In February of 2023, a group of astronomers announced the discovery of a ring around Quaoar, making it the third non-planetary object with rings after Chariklo and Haumea. In April of 2023, another group of astronomers discovered a second ring around Quaoar. I'm probably not saying that right, but please correct me if I'm not. Unlike other rings in the solar system, Quaoar's rings orbit beyond its Roche limit, the region where its gravity would rip apart small objects to potentially form a ring. I'm probably going to show you guys what that is if you don't know. So, if we get a random small moon, and oh wow, Quaoar is really small. Okay, I did not. Oh wow, it is actually really small. Probably gonna need like a Mimas. Yeah, Mimas. Okay, if we put Mimas like here, Oh wait, yeah, I forgot that. See, it's getting ripped apart. That's what Rouge limit is. So, if you didn't know. Alright. Rings, beyond this limit, rings are thought to coalesce into small moons. So, like, it would become way what? Yeah. So, alright. So, instead, astronomers think that Quasar's narrow rings are made of icy particles bouncing off each other, preventing a new moon from forming, and are held in place by a gravitational balance between the dwarf planet and its moon Waywat. Okay, and yeah, that's still going on. Might as well just get, yeah, just buy rings. Say bye to the rings. Okay. Okay. Just turn it into a star. Just turn it into a star. Yeah. 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 What? What in the... So everything's gone, but the solar system isn't being affected? Wait. So the solar system isn't being affected by this thing. I'm very confused, but and also what? What? How far away? What? Huh? Wait. Yeah, they got pushed out. It's like half an astronomical unit, and then this is like... No, it didn't get pushed out, but the Earth is gone, and Jupiter's and Saturn and... On to the next one, because I'm very confused. Okay, but anyways, we've also added a simulation of the dwarf planet Haumea's rings, which were discovered in 2017. Okay. Ah, okay. Oh, Haumea has 2 moons? Okay. Haumea is a dwarf planet discovered in 2004 that orbits the Sun beyond Neptune, also called a trans-Neptunian object. In January of 2017, it passed in front of a bright star, an event known as occultation. Is that how you say it? But by measuring how much the star dimmed while Haumea passed in front of it, astronomers detected that, like Chariklo, Haumea had a ring around it. Haumea is the first dwarf planet to have a ring around it. Quasar is the second, and the second non-planetary object to have a ring in the solar system. So, I'm pretty sure if we add something like small, like Chariklo, this asteroid, and we put it here, it should get torn apart by Rouge limit, and technically over here as well. So let's check. That one's getting torn apart, but I'm not sure about this one. Universe Sandbox isn't completely realistic, so it might not. Oh, okay. Okay. Okay, I see how the ring was formed. Maybe something like further inwards. Maybe it was something further inwards that kind of went out. See? Like there. You can see my mouse. The fact that the rings are actually still holding on. Still orbiting. Just... Oh! Oh, okay. Haumea's smoking up now. What happened if we, you know... Come on, come on. Yeah. 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 Come on. Wait, how does this thing still exist? Honestly, I just broke the game even more. Anyways, manipulate the temperature of the universe and learn about the cosmic microwave background, a type of faint radiation spread across space. Okay. Cosmic microwave background, or CMB, is a type of faint radiation spread across space dating back 13.4 billion years ago to when the universe was just 370,000 years old. Human eyes can't see this radiation, but we can simulate its effects in Universe Sandbox. Oh my god, wait, what is that thing? The coldest possible physical temperature in the universe, known as absolute zero, is 0 Kelvin or minus 273 degrees Celsius. However, the cosmic microwave background warms everything by 2.73 degrees Kelvin, so the coldest any object in the universe can naturally be is negative 270.42 degrees Celsius. If you live in the US or anything, or anywhere else that doesn't use Celsius, just like put it into like Google, like measurement or thing that converts Celsius to Fahrenheit. Okay, but anyways, in Universe Sandbox we used a background temperature to simulate this radiation and heat all objects by a constant 2.73 degrees Kelvin. But what would happen if our solar system, if the background temperature was higher? When the cosmic microwave background first appeared, when the universe was young, it was about 3,000 degrees Kelvin. That seems like a good temperature to try. Okay, keep an eye on Earth while we increase the background temperature. Click on Sim, Advanced, okay, and okay. Alright, this doesn't bode well for life on Earth. Yeah, definitely doesn't. The background temperature is now an intense radiation throughout the universe, hot enough to emit visible light like a star, turning space orange and heating the planets. In real life, the expansion of the universe has caused the cosmic microwave background to expand over the last 13.4 billion years. Luckily for us, this expansion has made the radiation from the cosmic microwave background less energetic and cooled it from 3,000 degrees Kelvin to a more comfortable temperature of 2.73 Kelvin. Now that you know a bit more about the cosmic microwave background, try seeing how hot the background temperature needs to be to vaporize the solar system. Alright, let's, god, that's blinding, and now it's becoming nice again. I mean, not nice, but yeah. Not nice, but sorry. Oh no. Yes. Oh, what's going on? What have I done? Where is everything? Where is everything? What? Okay. And now we do search for pairs of supermassive black holes. Oh god. At the center of every galaxy is a supermassive black hole millions or even billions times the mass of our sun. But despite their size, these monsters of the universe are very hard to observe because they do not emit any light. In fact, the supermassive black holes at the center of the Milky Way, Sagittarius A, shown here, wasn't proven to exist until 1998. So how do we search for these celestial behemoths? Okay. One way is to look for pairs of supermassive black holes that form when two galaxies collide, instead of looking for individual black holes in each galaxy. After these galaxies merge, their central supermassive black holes gravitate together to form a binary system that gets closer over millions of years. I am still zooming out. Okay. As the supermassive black holes orbit, they emit gravitational waves, ripples in space predicted by Einstein's theory of general relativity. These gravitational waves are easiest to look for when the supermassive black holes orbit once every few months or years, like those shown here. So supermassive black holes can be found by looking for these specific gravitational waves. We do not simulate gravitational waves in Universe Sandbox. Okay. Oh god. We need a detector much larger than we can build on Earth to observe these gravitational waves. In fact, we need a detector the size of a galaxy. This is because many orbits need to be observed to be sure that the signal is from gravitational waves. Since these orbits are long, a detector that spans thousands of light years is needed to capture many orbits. Okay. A detector is called a pulsar timing array and consists of many pulsars, rapidly rotating neutron stars that emit beams of radio emission like a lighthouse. Pulsars rotate extremely regularly, and astronomers can accurately predict when the beam of emission will sweep across Earth to within tens of nanoseconds, making them sensitive to even tiny changes in the predicted arrival time. As gravitational waves move through space, they squeeze and stretch it, changing the distances between the pulsars and the Earth. This causes the pulsar emission to arrive slightly earlier or later than expected. The signal of the gravitational wave signal, the strength of the gravitational wave signal increases as these delays are observed across the pulsar timing array over many years. Okay. So far, astronomers have not found any individual supermassive black holes using this method, though they are looking. However, on June 28, 2023, evidence for these gravitational wave background signals, the collective signal of gravitational wave emitted by every pair of supermassive black holes in the universe, was announced by the North American Nanohertz Observatory for Gravitational Waves. And also, it says my simulation can't run fast. I wonder why. This signal will allow astronomers to learn more about how supermassive black holes at the centers of galaxies form and how galaxies merge and evolve. In the future, astronomers will be able to analyze these gravitational waves to find individual supermassive black hole pairs using this method for the first time. This evidence opens up a new way of seeing the universe where astronomers can search for gravitational waves from individual pairs of supermassive black holes, further understand the gravitational wave background signal by collecting more data from pulsar timing arrays, and learn more about how galaxies collide and supermassive black holes form. The future is sure to reveal more about these gargantuan black holes than we have ever imagined. Okay, now how fast was it meant to go? Okay, a few hours, a few days, a few months a second, a few years a second. Okay, so like 20 years a second. Go. Oh, that is... that hurts my eyes. But... wait, how close is the closest... wait, so how close... Oh, God. Oh, God. Okay. How close? Closest... So if we do this, so like a few hundred light years, so we're fine. Okay, got it. I wonder how... anyways, oh yeah, I forgot. The subscribers galaxy, it's probably ended by now, so, like, almost ended, so, where is System A? I've been playing Universe Sandbox a lot, okay. System A, no, it's gotta be up here, so order save, order size comparison, System A. This is what the subscribers galaxy looks like. If once this stops, okay. So, I feel like that's barely in an orbit. Like, if you see, that is barely in an orbit, but it says it isn't. Actually, yeah, wait, if there's nothing, wouldn't it always be in an orbit, or no? Actually, no, I'm not going to change the velocity because that would, but here is everyone that's in the subscribers galaxy. We've got Atish Kank 4A444. Okay, just the star. We got Hestia with the amazing rings and with its moons. Okay. And also, for some reason, some really spread out rings. Okay. But anyways, we got J1407B. I think you know what that is. So we got MG Life LBS. So if we, there we go, we got the sun and we got the moon and we got the earth. Okay. Jackson's stuff 374. It's probably around the sun. Yep, solar, which was every planet in the solar system combined, I think. Yeah. and Suvis, which is the combination of a bunch of moons. You can actually kind of see them, like Ganymede showing, and then there's some Callisto. No, it's more Ganymede, but yeah. Next, we have all of these. We got the random Earth that I placed, Polek, which was actually one of the first, so let's go take a visit to Polek B. Now this brings back some memories. It's not like this channel's that old, but yeah. We got Fabienne 247. What? Okay, so, and we have its rings. And with a bunch of stuff, okay. And then an escaped moon, I guess? Okay, but next, I'm pretty sure this was the first one. Sub for diamonds, so let's take a look at this. So Super Earth, it was a Super Earth with a habitable small moon with a huge storm going on. Wow. Okay. Sadly, it was too close for life, 168 degrees, but okay. Next, we got Prime 10199 with a gas giant, so most likely some moons, yes. This one, and then little moons, and then 3 asteroids. Alright, got one Ovdu tile, and then an insanely large number. Ericurni, okay. Hot planet, and then Akam. Another burning planet, but this time would actually, and then we go War with 2 R's, which I'm pretty sure was from the last one. A hot Jupiter, like very hot. War C, okay. Habitable planet, but not so habitable. War D, this one's like actually habitable, slightly. And then War E, which was the one I tried to make habitable, but oh, it's still like, you can see the water. If you just like do that, you can see the water kind of settling. Okay, there we are. We got the war planets. Next we got Hampered with their planet here, Hampered B. Nice. Rataskina, Orapax, and Curio. Okay, we're getting really close. This is the final 2. We got William with the tidally heated planet. Did I succeed? No, but at least it's not net minus 270, so I slightly succeeded. Yay. But I mean, like, it's a tundra planet, yes, but life still could find a way. And then Fabienne Chaven with the super red dwarf. Wow. Okay. With some planets habitable. Yep. A random known planet, I think. Osta and another gas giant. Got it. And then Finally, we have this cool planet which was meant